Hi everyone, I'm Finnbar. I'm a PhD student at the University of Warwick, and today I'm going to talk to you about transforming proc notation AFRP code into imperative code. Also, we're dealing with loops again, because apparently loops are my nemesis after last year's paper. There are a lot of words there, so we're going to start with an example of what Arrowized functional reactive programming actually is, and then hopefully we'll all get up to speed and that should be all good. If you saw my talk last year, I nicked the example from there. Sorry, my thesis is due soon, so I had to take what I had access to. So here's a robot that I found, and we're going to write an AFRP program for working with it. We're going to give it a pair of sensors, a distance sensor and a touch sensor, to determine if there is an object within my grasp and how much I am grasping that object if I'm already grasping it. And we're going to give it a single gripping motor to say that we can control to determine how much we grip it. The question then becomes, given my sensor values at some time step, what output should I produce? Given a touch and a distance reading, what should my gripping motor be set to? So you might sit and think for a while and come up with a program with this kind of structure, where we have these distance sensor readings being checked by this isObject predicate to determine if it sees an object to grip, and then the touch sensor readings being checked with this isGrip predicate to determine if there's already an object being gripped enough, and then use those together to determine what the motor should be set to. And this is very similar to how AFRP is structured. We have signals, which are values that are updated at each point in time, at each time step. So at every 60th of a second or whatever, our touch sensor will be updated with a new reading. That signal will have a new value on it. And then our boxes are signal functions, which are the main abstraction in AFRP. These take our signals, transform them into new signals, allow us to react to our inputs to produce our outputs. Now, because this is Arrowized FRP, we're using the arrow combinators to build our signal functions. I'm going to quickly go through the arrow class now to talk about, what we're doing. So the first one to talk about is the R constructor, which takes a pure function and lifts it into a signal function. What this does in an AFRP world is says every time our input signal is updated with a value, run some pure function on it and produce that as the new value on the output signal. So in this case, we've got this little distance less than 30 predicate to check if the object is close enough. Oh God, I pressed home. Hang on. OK. Next thing we have is parallel composition, where we can take two existing signal functions and run them in parallel. They take in the parallel composed version, takes in a tuple input, runs the first of that tuple on the first signal function, and the second of that tuple on the second signal function, producing a new output. And finally, we have sequential composition, where you pass the inputs of your first signal function the outputs of your first signal function as the inputs to the second. So in this case, we're taking our isObject and isGrip together and passing it into grip to get the final result of our program that we showed earlier. Great, fantastic. That's all we need. Great, I'm done. No. So this is great for small programs, but when our programs get larger, we end up dealing with a lot of these combinators, and it can get quite difficult to read and difficult to understand. So we have this nice notation called proc notation, which provides a convenient syntax for referring to our signals and not worrying about routing at all. We just say what we are going to be applying our signal functions to. So in this example, we've got dist and touch as named signals, as our named inputs. And then we have this little weird, I don't know how to pronounce this arrow, which runs a signal function with the input signal. So we can see this is much clearer. It's obvious that we have this SEES-Object that we're passing to grip and this HasGrip that we're passing also to grip. Great. The issue lies in how this is desugared and what the code that we end up with looks like. Here is a surprisingly simplified version of what this code desugars to. How it works is it takes each line of our existing code and uses R's between each of these lines to reroute the code such that the right inputs are being passed to the right outputs. So in this case, we run isObject, and then we use an R to swap our inputs about, and then we run isGrip, and then we use our R again to swap his inputs about, and then we finally get to run grips at the end. That's a lot of routing code. Like previously, we only had the stuff in gray, but now we have all of this extra stuff which is run at every single time step to reallocate, to allocate a tuple, to swap these inputs about. Generally, it's not great. So the question becomes, can we avoid all of this routing code? Can we avoid all of these tuple allocations? And the answer is already in the literature, fortunately, with Chopin and Nelson's Scalable FRP. They have a solution in two parts. Here is a diagrammatic version of the desugaring code I just showed you. As you can see, we've got these big R blocks now that are messing us up. The first thing they do is replace these R's with special routing combinators. Today, I'm just going to use these bendy arrows to show them. Don't worry about how exactly they're represented as code. The key here is that they are separate from R. They give us an idea of exactly what inputs are connected to what outputs, rather than just being this black box. The second thing they do is represent signals as memory cells instead of just Haskell values that we pass around. So as a single pass from inputs to outputs, the SFRP compilation process gives memory cells to the inputs, and then with each new output we see, we give it a new memory cell. So every wire in this diagram, every signal that we're routing has a memory cell associated with it. Then our program, we create an I/O computation for each of these signal functions as we're doing this. So when we encounter isObject, we both allocate this M3 memory cell, but also create a little computation that performs what the signal function should do. In this case, we defined isObject to check this predicate, so that's what we do. We read the input memory cell M1, and then we check that predicate on M1 and write its result to M3. Cool. This means that rather than doing all these tuple allocations where we're messing about with routing and R's and that sort of thing, we just write to memory cells. We start by writing the inputs to our input memory cells, M1 and M2. Then we run each of these computations in order. So we just get true in this case. Let's say we get false. And then at the end, we just read the output memory cell to get the results. No more tuple allocations, no more copying, just reading memory cells. So that's great. Why am I here? What am I here to talk to you about then? Well, we're going to have a brief look at the loop combinator in AFRP and how this makes things difficult for the process we just showed. So here is a simple example of a loop. There are two new combinators in here that I haven't told you about yet, so we'll quickly go through those. First of all is this delay operator called pre-0, or you can put any value within instead of just 0 in the pre. It takes in some input signal, and then its output signal is that same input signal, but delayed by one time step. So for example, if I have a signal that takes values 1, 2, 3, during the first 3 time steps, the output of pre-0 becomes 0. We prepend 0 to the start of the signal for the first time step, 1, 2. So yeah, this is just a nice delay. The other combinator we have is loop, which creates, well, a loop in our graph. We have, given some signal function, it connects its second output back to its second input, thus creating a cycle. This is a really useful pattern because it allows us to take previous outputs, because we're delaying them by one time step, and pass them back in as inputs for the current time step. And to give a brief example of how this works and how we run this, because it kind of looks like we have a dependency cycle if you squint, I'm going to go for a brief example. It turns out this example just sums the signal over time. So given some signal to sum, at each time step, whatever value that signal takes, we're going to add it to a cumulative sum and output the total sum as a new signal at the end. So let's say we get in 1 as our input. Pre-0 prepends 0 to the input signal. It does not need to know its input yet, and this is sort of a key reason as to why there's no dependency cycle here. It doesn't need to know its input yet. It can just prepend that 0 without worrying. So that means we have both of the inputs to our on curry plus, means we get 1, and that's the output for the first time step. Then, okay, cool, we get a second input, 2. Now, pre again can produce its output without its input because we got it at the previous time step. It's 1. So pre-0 produces its output, gives us 1, we get 3, and so on and so forth, and you get your cumulative sum. So great. Let's now apply the SFRP transformation and see why this is suddenly a bit more complicated. So, OK, we have some input memory cell M1. We're already a bit stuck because we need some input to the R on curry plus. Cool, that's fine. We'll just make an M2. Don't worry about it. OK, so we'll now make some computation that reads from M1 and M2 and writes to M3, which is our newly allocated output. Then cool, we're going to do pre-0 again. We've got an M3 as input. We'll create a computation. We'll output M4. And then our program as a whole is run just by writing to M1, run SF1, run SF2, done. Except there's a few problems. So by doing this in a single pass, by going through our signal functions and allocating computations and output memory cells for them, we first end up with this weird mismatch where this loop back edge, this single signal, is represented by 2 different memory cells, M2 and M4. This is not ideal, but it's an easy enough problem to fix. We could add some copy operation from M4 to M2. We could perform some kind of global rename, whatever. The real issue lies with what order these computations should be executed in. If I say, OK, let's run SF1 first, like we said, M2 is now uninitialized. We don't have its value. If we were to run it later time steps, we would have the wrong value. Similarly, if we run SF2 first, then M3 is now uninitialized. So we're stuck again. This method has an inherent problem with loops and cycles that means we need to rethink this. And that's what our paper's about. How do we take an AFRP program, compile it to I/O computations, and order them such that the loop expression works correctly? And the trick is multiple passes rather than just a single pass transformation. So we're going to go through 3 passes. The first, we're going to assign memory cells just like we did in SFRP, but we're also going to fix this loop issue by unifying the memory cells on these loop back edges. This is fair enough. Then we're going to create computations for each signal function, and only at the end are we going to then order those computations based on their dependencies. Let's go through this in more detail. So for this part, we're going to look at a slightly more complex example, just because it means we can look at more memory cells, and it's just a bit more helpful. First, we assign the memory cells like we did before. We started with M1, we built this M2, we went across allocating outputs. Lo and behold, we're there. Then we unify cells allocated to the loop back edge. In this case, it's pretty easy. We're just performing a global substitution of M9 in place of M2. When you get routism, when you get these these bendy arrows involved, the substitution becomes a bit more complicated, but we don't need to worry about that. It's just a global substitution. Now we're going to look at RG, and we're going to look at Rs and Pres separately to get an idea of how exactly we need to order these. So for our Rs, we're just going to do what we've said that we've been doing the whole time. We're going to read in the inputs, M3 and M5, perform some computation, or perform some calculation, in this case, run the pure function G, and then write its outputs to its output memory cells. Great. The question becomes, when are we able to run this computation? Because we sort of hand-waved earlier that we can't run these in the order, it becomes much more difficult for loops. Well, once M3 and M5 have been updated with their value at the current time step, so once we've already written to them, we're allowed to run RG to update M6 and M value to their current values at the current time step. We state this as for a given memory cell, read it only after it has been written to. So there's this writes before reads dependency that we're working with. Pre is slightly different, and we're going to take a slightly different approach to this. At the start of the program, we're going to write this v value, the first value that the pre produces, to its output memory cell. And then at the end of each time step, rather than trying to do it within the Rs, at the end we'll update it. We'll update that M5 with whatever value it got in as input. So update that output cell at the end of a given time step, update its output cell with the value that it should take at the next time step. This has dependencies in reverse. So once M4 has been updated, we can run prev only after M5 has been read, because if we do it before, then we're reading a value from a future time step. We want this to happen right at the very end. We're going to call this an after write, because if I keep saying write, it'll get confused with the other writes that we do in R. Sorry. And we're going to say that for a given memory cell, you can only after write to it once all reads to it have been completed. So what we've seen is we now have two types of dependencies on values. During each time step, a cell must be read only after it's been written to, but a cell must be after written only after all of its reads have been completed. Yeah. So with this, we can build a dependency graph to identify exactly what order these computations should be run in. For example, here, we're adding this edge between RF and RG for this M3 memory cell, because RF will want to write to this memory cell. It wants to write its outputs. But RG will want to read it, and thus, because writes before reads, RF happens before RG. It's a similar situation for M4. RF wants to write, preview wants to read. For M5, things are a bit different, because we want preview wants to after write to this, so it must happen after RG has read it, and therefore RG must happen before preview. You go for all the memory cells, you get a graph like this, and then you just perform a topological sort to get a correct ordering if there exists one. In our implementation, we do a strongly connected component search, because we need to double check there are no dependency cycles, otherwise there's no way to order these computations, and everything would break horribly. We don't want everything to break horribly. For the rest of the talk, I'm going to talk about an implementation using a previously published technique called Rearrange. Here's our simple loop again with the I/O computations we talked about before. So again, R+ is reading from M1 and M2 and writes to M3, and pre0 is reading from M3 and writing to M2. What we're going to do, or we're going to use the rearrange technique to annotate the types of these computations. So in this case, the writes and reads are annotated using these type level lists with representations of the memory cells being used. So in this case, we have 1 and 2 being read, the type says so, and we have 3 being written, the type says so, and similar for pre. This doesn't solve our issue, though, because, as we said, if we want the writes of pre to be happening later than the after reads and the writes for R to be happening before, this is why we call them after writes. Oh, yeah, I said that. But the rearrange technique has this nice property that it can take these computations and order them at compile time so that these dependencies hold. So we extended it. We've added a third entry for after writes into our types. We've added this write after function for specifying these after writes, and we extend this ordering mechanism so that then these after writes happen, well, after reads. And in the same vein as with rearrange, if we see a dependency cycle due to these dependencies, we throw a compile time error. Nice. I'm going to briefly talk about how we transform our AFRP programs into these computations, because given they're annotated at the type level, you can imagine we have to do a little bit of type level magic. Oh dear. So how we do this. We represent our AFRP programs using a GADT, but we're going to annotate them at the type level with their structure. So R's are now annotated with this rcon constructor, pre's are annotated with precon, the composition operator is annotated with composition of those two annotations, and so on and so forth. So you end up with a type kind of like at the bottom. Notably, this is fully inferred. You don't have to worry about this. By using this GADT, you automatically get this structure at inferred for you. Then we're going to annotate the type of the signal function with the memory cells used. So we have this assigned memory type class that, given some SF with type level structure given by this con and input and output type, we're going to get an annotated version of con. This will look something like this. Don't worry too much about the details. The key thing is we have all of these memory cell representations now here in the type of the program. Also, this is fully inferred, or we have a functional dependency here, which means that if we have the type of the input SF, which we do because it's fully inferred, we can get this annotated type. Then we transform this annotated type into the grades of those computations we showed earlier. So again, functional dependency means that we have this annotated structure, input and output type, and we get a heterogeneous list of the computations. I'm not going to worry too much about exactly what the type looks like, but it effectively looks for each archon and precon and builds the respective type from the memory cells that it sees. Then we just throw these at rearrange. It orders them all for us. We're sorted. Finally, I'm going to talk about some results from our implementation. What we did was we generated a random corpus of proc notation programs. These programs use rec, which desugars to a use of loop, hence why we needed to do all this fancy stuff with loop. We parameterize this in two ways. We have the length of the program in number of lines and the fraction of that length which is within a rec, so which would be in this loop. So we're varying both the length of the program and how much of it is loopy, effectively. And we get some nice results. We find that our implementation, Oxbow, performs significantly better than Yampa in all cases. The bracketed number here is the rec fraction. Notably, Yampa's performance gets worse as you make the loop bigger, regardless of the size of the, regardless of the length of the code. Oxbow does not have this problem. It's performing the same number of computations regardless. Well, yeah. We got some really good results for these fairly short program lengths, but we found that the GHC crashed when given these larger programs, in part due to this type-level representation that we're using, which is, of course, just a consequence of doing type-level stuff, as is tradition. We did try with a runtime version, and it worked fine. Like, it produced some, it can produce some runtime errors if you give it a program with an ill-defined loop, so one without that pre. But otherwise, it works well. So yeah, in conclusion, we showed a technique similar to Scalable FRP for taking AFRP code containing loop expressions and turning it into imperative code. And we've briefly talked about this implementation that uses this rearrange work we did. In the full paper, we have some nice stuff about exactly how the implementation works, including all of the code, well, most of the code, how we desugar proc notation, and how we generated our corpus of random programs that we built. Thank you very much for listening.
There's time for questions.
Oh.
Hi there. Yeah, really nice work. So you mentioned at the end there that you can check for like the well-formedness of loop expressions.
That's right.
And you mentioned like, you check for the absence of like a pre, so like if you have like an undelayed loop there. Is that something that you check, or is that something that's already been checked in like in the ordering process? Like, do you need to check it again, or? It's
checked in the ordering process. So when you get, let's say you have a cycle only containing these R's, you kind of get the problem we showed before where, okay, so if I have, how do I do this without illustrating, without a diagram? RF, RG, RH composed, and then a loop from RH back to RF. Cool, so F wants to read from this, G wants to read from this, H wants to read from this, F wants to read from this. You get an infinite cycle, and the ordering process will get a cycle in the dependency graph because F depends on G, depends on H, and so on and so forth. And rearrange will just complain. It will go, nope, I can't compile this, I cannot order this because there is a dependency cycle in what you've asked me to order.
Okay, and this like dependency checking, was it possible for it to get stuck? Because it almost sounds like it's like, it's not a semantic check, is it? Is it just checking it structurally?
What do you mean? So sorry, in terms of how the implementation looks at the types and builds a dependency graph, or?
Right, yeah, like is it possible for this to get like stuck in a loop of some sort where it can't resolve the dependency, or does it know like if it's already visited like a source that it's already seen before? Mm-hmm.
So it performs a strong connected components check which guarantees that there are no dependency cycles. if the strongly connected, so many words, if the strongly connected component check finds a strongly connected component of size greater than 1, there is a dependency cycle because there must be a cycle for it to be strongly connected. It will check for that first, and then if that fails, it will immediately throw a compile error, and it won't attempt to perform any infinite cycle dependency checks.
Okay, great. Thank you.
All good.
So I also want to ask about cycles that are ill-defined.
Yeah.
So when you're generating your random programs,
Yeah.
I wonder, did you generate random programs that lacked cycles by construction?
Yes.
Or did you, you generated, okay. So in that case, you haven't tested that your application, your system rejects random programs when there are cycles.
We tested a bit by hand, but I don't have a formal set of results on sort of randomly generating programs with ill-formed cycles to show.
Right, okay, it would be interesting to do that too. But then I would have asked you what proportion of programs contained undefined cycles.
Oh, in terms of like, so what if I generate a random program? What's the chance of it having an undefined cycle? That sort of thing, or?
Yes, exactly. Or rather, how much of your testing effort are you spending on testing that you reject programs correctly, and how much are you spending on testing that you compile programs correctly?
Got you. In which case, yeah, that's something we should do. That's a really good idea. Thank you.
Really nice work.
Thank you.
So one thing I'm wondering was, if you go to imperative program and use your memory cells, then you basically get rid of the problem of normal AFRP that you may introduce as a memory leak. So have you considered to maybe also go back to a lazily evaluated program, but constructed in such a way that you wouldn't introduce a memory leak that way?
Oh, so what? Go from a imperative version back to a version using R for routing and that sort of thing, and
directly go back to a lazily evaluated program, but use the freedom to now modify the evaluation order via laziness.
That's really interesting. We haven't considered that at all. Okay. That's a really cool idea. Thank you.
Thanks.
Cool. Well,
Okay, last question.
Okay. So that's the arrow desugaring, the one that's in GHC right now is annoying and stupid.
Yes.
You want bifoldable and not. So when you use proper combinators for the programs that you now give to Yampa, does it do better if you, instead of all of the first and then swap and then another first and then swap and just say, you know, the 3 stars operator, does it perform better or worse?
so is this a question of if you just replace R with these routers, does performance improve?
Yeah. Whether how much.
So we haven't put much testing effort into that.
Okay.
My expectation is it doesn't really improve because you're still performing these tuple allocations. Like the only way to implement one of these routers in standard AFRP is to match on your input data and create your output data, which is inevitably going to be a tuple because that's how AFRP does this sort of routing. Is there a way to do it without using memory cells in general? Maybe. There might be some like unboxed tuple stuff that I haven't thought. I did like try and experiment with it briefly and got scared off by the syntax, to be honest. But I think there might be an unboxed tuple solution that means that you would be able to do that, but I don't know.
All right, thanks.
Thank you.
All right, thanks again, Finnbar.